We looked at linear equations one at a time in the previous section or two. Linear equations, applications of linear equations, including linear functions. If we have an equation with two variables in it, such as x plus 2y equals 8, we consider the graph of that, and the graph is basically the picture of the solution set. We're looking at a bunch of points on the straight line, and what that means is that we pick any one of those points on that straight line, the ordered pair is going to satisfy the equation. So if we consider the two equations, or at least two equations at the same time, what we're considering is a system of linear equations. X plus 2y equals 8 and 2x minus y equals 6 considered at the same time is a system of linear equations. Now, any one of the linear equations is going to have infinitely many solutions. I've just listed 5 or 6 solutions for each one of these, but we know each one has infinitely many points on it, so infinitely many ordered pairs would satisfy it. If we consider the picture, it's easier to answer this next question. But is there an ordered pair, do you suppose, that satisfies both of these equations? Because that's what we really need. If we've got a system, x plus 2y equals 8, 2x minus y equals 6, we want an ordered pair that satisfies both of those. And if we can find such an ordered pair, we could classify that as a solution to the system. So what do you think? Might there be such an ordered pair? And if so, what's it going to be? Well, if we consider some of the ordered pairs that are given, we might check to make sure they actually work. 0, 4. 0 plus 2 times 4, 0 plus 8 is 8. So that works in the top equation. If we consider the intercept on the x-axis, 8, 0. 8 plus 2 times 0, 8 plus 0 is also 8. So that satisfies it. And since we know the equation has nothing but x terms, y terms, and constant terms, no x squared, no y squared, no x's or y's to other powers or x or y's in the denominator, no radicals, it's linear. So we connect the dots with a straight line. When we do connect the dots with a reasonably straight line, there we go. Connect the dots with a straight line. We notice that these other points are on there as well. 2, 3, there's 2, and there's 3. And 4, 2, there's 4. And there's 2, and 6, 1, there's 6. And there's 1. And of course, 8, 0, and 0, 4. And many, many other ordered pairs satisfy this because many, many other points, obviously, are on this straight line. If we go to the other linear equation and see if we can sketch a graph of that, 2x minus y equals 6. The y-intercept is given at 0, negative 6. Confirm that. 2 times 0 is 0 minus negative 6. That's the same as 0 plus 6. That's 6. So, got to go lower than this. Negative 5, negative 6 is right there. And then how about the x-intercept 3, 0? That would be about right there. That works. 2 times 3 is 6. 6 minus 0 is 6. And so we've got that straight line. Okay. What we're looking for is an ordered pair that satisfies both of the equations. So what we're looking for is a point that resides on both lines. Is there one? Looks like it. You're thinking maybe, I'm thinking it's 4, 2. The way my graph is drawn, it looks like 4, 2.5. But 4, 2 is the one that works. If we take the 4, 2, 4 plus 2 times 2, 4 plus 4 is 8. So it satisfies the top equation. And if we take it right there, 2 times 4 is 8. 8 minus 2 equals 6. So it's an ordered pair that satisfies both equations. It's a point that's on both lines. So one approach to solving systems of linear equations would be to graph both lines and look for a point where they intersect. And if there is such a point, that would be the solution to the system. And if there's not, then we say there's not a solution at all. If there's more than one point that's on both lines, that's kind of weird, but it can happen in an extreme case, then we might say that there's more than one solution to the equation. Speaking of extreme cases, there are actually three different scenarios we might consider when looking at these systems of linear equations. Three cases for two linear equations. AX plus BY equals C, and let's call it DX plus EY equals F. Three cases. Case one is the one we just looked at. Each one has a straight line for its graph, and the lines have different slopes, different amounts of steepness to the lines. If the lines have different slopes, then maybe one looks like that, and maybe one of them looks like that, and there's exactly one point that they have in common. That's case one. Case one we call pull it back. There we go. Case one, we call this a consistent system. And we call it a consistent system. That means it has at least one solution. If it had no solutions at all, and that's the next case, we would call it an inconsistent system. But it's a consistent system, no contradiction here. It has at least one solution. But there'll be another type of consistent system that we want to distinguish this from. So we're going to call this a consistent system with independent equations. Consistent system with independent equations. Basically, that means if I take away one of the equations, it's going to change. It's going to change the solution set. So we need both of them. They contribute different amounts of information to the system, independent. So the solution set looks like this. There's the point where the lines intersect, AB. So the set, that's the solution, A comma B, an ordered pair. So the set that contains all the solutions to this system is the set that contains the ordered pair AB. That's what it looks like. And it was 4, 2 in the previous example. That's case one. Case one. Then there's case two. Case two. Case one, they have this. In case one, they have different slopes. In case two, they have the same slope. Imagine two lines having the same slope. Maybe one of them looks like that. Maybe the other one. Whoa, not that. Maybe the other one looks like that's close enough. Looks like that. These two lines, if they have the same slope, are going to intersect in exactly how many points? 0 points. They don't intersect. If the one below, bottom line, were steeper, it would catch up with the top line. If the top line were steeper, down in the lower left somewhere, they would intersect. But if they're exactly the same amount of steepness, same slope, no point of intersection at all. The empty set is the solution set to this system. If we're looking for an ordered pair that satisfies both equations, there's not one. Because there's no point on both lines. We call this an inconsistent system. And then there's case three. What other possibility is there? They have different slopes, and there's one solution. They have the same slope, and there are no solutions. Yeah, on top of each other. They have the same slope and the same everything else. Y-intercept, X-intercept, every other point on the straight line is the same. And so it looks like that. And that. Okay. If that's the case, the equations themselves could look different. but the lines are exactly the same line when we graph them. This is a consistent system because pick a point, any point on this line that is the graph of both of them, it's going to satisfy both of them. So any point on that line, not any point in the plane, but any point on that line is going to satisfy both equations. So it's going to be a consistent system, but there are infinitely many solutions, so we say the equations are dependent. And in this context, it means they contribute essentially the same information. So if we throw one of them away, we'll still have the same solution set. What does that solution set look like? There's more than one way to write it. The simplest way to do it would be to look at the two equations and realize that they are equivalent, so that all we need is one of them. We don't need both. We look at the both, we pick whichever one we like better. Maybe it's the one with the A, B, and the C in it. And we say the solution set is the set of ordered triples of the form x comma y such that ax plus by equals c. That'd be one way to write the solution set. It's maybe not the most constructive way, but it does convey the answer there. If we wanted to be a little bit more constructive, we might take the equation and solve it and put it in y equals mx plus b form. We might write it like this: the set of all ordered pairs of the form x comma y such that y equals mx plus b. And I could have taken that particular equation and solved it for y in terms of x. I think it would have been y equals negative a over b times x plus c over b. But we didn't want to go there. Just solve it for y. Put it in slope-intercept form, whatever that looks like, with the numbers that you have, and that's what it would look like. That may be adequate. We'll probably work an Alex problem before we leave today. But one further thing you could do that's maybe even a little bit better, because it only uses one variable, is to say the set of all ordered pairs of the form x comma mx plus b such that x is any real number. Set builder notation, we indicate what the solutions look like, the form that they would take, and then if there's a variable in there that could take on different values and consequently result in different solutions to the system, we indicate the different values the variable might take on. It could take on any real number. So we'll look and see if we run into a dependent system, and we will. There's at least one in here. We'll look and see how to write the solution set using just one variable rather than having to use two. It's more constructive because one thing to say the solution set has infinitely many elements, or there are infinitely many solutions to this system. It's another thing to say, okay, well, let's find a few. Let's find a few. There are infinitely many of them. We ought to be able to find at least two or three. What's a good constructive method of substituting something and figuring out what those solutions are? So that's a more constructive way of writing the solution set there. Example 1. Okay. Going to throw 3 rocks at the same bird here. Take this system and solve it 3 different ways. I'm going to solve it using the substitution method, solve it using the elimination method, and then finally solve it using a graphical method. I'm pretty sure this is case 1, although it's a close one. I think the slope of the top line, if I'm doing the mental math okay, is positive 1/3. I think so. Positive 1/3. Double check me on that. And I think the slope of the bottom line is positive 3/10. 3/10, like that. And those are pretty close. So if we were to graph this freehand without using graph paper, 1/3 and 3/10 are fairly close together. So it might be difficult at first to distinguish between these lines, unless we went way up to the right or way down to the left to see exactly where they started to move away from each other. It really won't matter. Using the substitution method or elimination method, we can find the exact solutions doing that. But if we're wondering, are we going to expect no solutions? Are we going to expect infinitely many solutions? Well, if the slopes are truly different, we won't. We'll expect exactly one ordered pair that satisfies both of these equations. Substitution method. If I'm looking at it and the method is not specified, and I'm wondering, would the substitution method be a good method to use? I look at the top equation at the x and the y terms. I look at the bottom equation at the x and the y terms, and I hope against hope, or if I'm still making up my mind whether I'm going to use the substitution method or elimination method, I'm looking for a nice coefficient of x. By nice, maybe air quotes would be appropriate. By nice, what I mean is a coefficient of x that's either positive 1 or negative 1. Or a coefficient of y, I guess. A coefficient of a variable. I don't have to specify x. A coefficient of y. That would also work. That's either positive 1 or negative 1. And what I see is a 10, a negative 3, another negative 3, and a positive 1. The positive 1 makes me happy. That means we can solve this using the substitution method without having to introduce unsightly fractions into the mix. And if we can solve the problem without fractions, I think that's way better than having to solve the problem with fractions. So I'm going to take the top equation, solve it for x. So step 1 in the substitution method, solve x minus 3y equals 8 for x, because that's the variable with the nice coefficient, okay? Coefficient of 1. When we do that, we get x equals 3y plus 8. No fractions. Had to be brought into the system in order to come up with that. So that's good. 2, substitute 3y plus 8 for x in the other equation. Negative 3x plus 10y equals negative 15. Basically, we need information from both equations stored or compacted into a single equation. And that's what we do. See, with the x equals 3y plus 8, what we're saying is on that top line, every x coordinate is 8 more than 3 times the y coordinate of that point on that line. Well, we take that constraint, we take that requirement and impose it on the other equation, and the other equation says, whoa, wait a minute, that's not true for every point on the line. Negative 3x plus 10 equals negative 15, but maybe it's true for one. Maybe there's one point on that line, negative 3x plus 10y equals negative 15, that satisfies the fact that the x coordinate is 8 more than 3 times the y coordinate. And if we impose this information on that, it's going to eliminate the x variable, and it's going to give us the y coordinate of the point for which that is true on the other line. So here goes, negative 3 times 3y plus 8 plus 10y equals negative 15. And step 3, it sort of kind of goes without saying here. We've got an equation, just the one variable, y in it. Natural thing to do, hopefully, if we're looking for both x and y, golden opportunity to find y. All right, so we just do it without even thinking, but I'll write it down nonetheless. Solve for y. So we do that. Negative 9y minus 24 plus 10y equals negative 15. This is nice. Combine the y terms and we just get y. And so y minus 24 equals negative 15. When we add 24 to both sides, y equals, is it 9? It's 9. So evidently 9 is the y coordinate of the one point on this second line that has the property that the x coordinate is 8 more than 3 times the y coordinate. Well, every point on the top line has that property, so maybe if that's the y coordinate of a point that's on both of the lines. So take that y equals 9, and substitute 9 for y in, well, at this point, we're hoping we're believing that y equals 9 is the y coordinate of the point that's on both of these lines. So it shouldn't matter, we're going to check it in both anyway, it shouldn't matter whether we use this equation at this point or this equation at this point. Maybe what we should do is just use the nicest possible version of either one of the equations at this point, and I think it's the one that solved for x explicitly in terms of y. So I would suggest that we substitute that for y in the equation x equals 3y plus 8. If we substitute it there, then we get x equals 3 times 9 plus 8. And this is nowhere near the standard viewing window because x is going to be whatever 27 plus 8 is. Maybe 35. Wow. So 35. So at this point, if we have not made a mistake, not like the radical equations or the rational equations where you do everything right and still get a wrong answer. At this point, if we've not made a mistake, this is 35, 9, the only solution. The only solution to this system. It's still worth checking because sometimes we do make mistakes. So we should check and make sure this satisfies both of the equations. Negative 3 times 35 is negative 105, I think. And 10 times 9 is 90. Negative 105 plus 90 is it negative 15? Negative 105 plus 90? I think that's negative 15. That sounds about right. Take 35 in the top equation. Well, 3 times 9 is 27. 35 minus 27. Well, that's certainly 8. That's how we got the 35 in the first place. We used that top equation, so it should satisfy that. So that is the solution to this system. And that's how we go about it using the substitution method. Now, in a situation where we look at the x term and the y term and the x term and the y term, and they all have ugly coefficients. Maybe they have fractional coefficients. Maybe they have decimal coefficients. Maybe they're just nasty. We might not want to use the substitution method because when we solve for one of the variables at this point, the right-hand side might have some fractions or decimals that we just don't want to have to deal with. So in a case like that, the elimination method might be a better way to go. So let me make a fresh copy of this and paste it right here. Let's look at the elimination method. I think it's our college algebra textbook. She may call this the addition method. So it does go by both names. Most textbooks that I've seen over the last dozen years or so have called it the elimination method. I think when I learned it way back when, it was called the addition method. Because basically the idea is this. We want to take the two equations, rig it up so that when we add the two equations together, hence the term addition method, when we add the two equations together, one of the variables gets canceled. Either the x terms get canceled or the y terms get canceled. Well, you need that to happen. And we're going to add the two equations to make it happen. Now, when it happens, we say one of the variables has been eliminated from the system, and so that's why it sometimes is called the elimination method. So it goes by both names, so just be aware that it might be called either one of these things. So we're looking, and let's just see how we might go about doing this. If we look at the x terms in each one, and we wanted to add the two equations together in order to eliminate them. Now, we have equations, so we have the luxury of taking one equation, either one, and multiplying both sides by a constant. And that will give us an equivalent equation. It won't mess things up. So if I want to multiply both sides by 2 or by 3 or by 19, I can do that and get an equivalent equation. So we've got the negative 3x. If we could somehow find a way to turn this into a positive 3x, some algebraically legal procedure that we can pull off and make that happen, Then when we add the two equations together, it would cancel. The x terms would be on our way. They would figure out y that way. Alternatively, I mean, that's probably going to be the way to go in this case. Alternatively, we could consider the y terms. It would take a little bit more work to eliminate the y terms because, again, I don't want to introduce unsightly fractions into the mix if I can avoid it. So I look at the negative 3y, I look at the positive 10y. It's good that they have opposite signs. I like that. But I'm thinking least common multiple of 3 and 10? 30? 30? So we'd need to tweak both equations. We need to multiply both sides of the top equation by 10, because I'm thinking we're going for a negative 30y, the top equation. Multiply both sides of the bottom equation by 3, because we're going for positive 30y, bottom equation, and then add the two together. The negative 30y, positive 30y would cancel, and we'd figure out what x is. And then we could go and look and see what y is. So that's kind of the plan with the elimination method. Might as well go with the easier of the two and just multiply both sides of the top equation by 3. So 3 times x minus 3y equals 3 times 8. 3x minus 9y equals 24. And then rewrite the system, replacing the top equation by this new equation here. 3x minus 9y equals 24. That's equivalent to the top equation. Negative 3x plus 10y equals negative 15. And just imagine somebody might have handed the system to us just like that. We could add the two equations together and get y. X terms canceled. Negative 9y plus 10y is just y equals 9 again. So we get y equals 9. Now at this point we've got a choice. If we wanted to, if we're in love with this idea of adding the two equations together and eliminating a term like that, we could go back and turn that into a negative 30y and turn that into a positive 30y, add those two equations together, and it's going to tell us x equals 35. Should we do that? Would it be somehow unsatisfying if we didn't do that? Or, what's our other choice? Take the 9, substitute it for y in either one of the equations. And we can still call this the elimination method because we got it kicked off by eliminating one of the variables by adding the two equations together. So we can still get by with calling it the elimination method. It's just now we've got it down to one variable left. We can substitute what we know to find out what we don't know. X minus 3 times 9 equals 8. X minus 27 equals 8. X equals 35. And so we write it down, 35 comma 9. That's the other way to go. I'm afraid there's somebody in the room other than myself who might lose some sleep tonight if I don't go back and eliminate those y's. Are my fears unfounded? Is it okay if we just walk away from this problem and just move? Okay, all right. We still, let's see if it's still on the clipboard. Yes, there it is. We still haven't done the graphical method. Let's do the graphical method. Graphical method, face value. I suppose if it were as simple as, let me fire up GeoGebra. GeoGebra 5.0. I know I wouldn't expect anyone else in the room to care about this, but it's deeply meaningful to me personally. GeoGebra 5.0 has been in beta since 2008. Think back to 2008. And I think this week they actually, it's been like 4.9.297, 4.9.298, just version after version of experimental. Finally, it's 5.0.0 or 5.0.8, something like that. Anyway, it's finally out of beta, and if it were as simple as, I forgot what the equations are now. If it were as, where are your equations? There you are. If it were as simple as typing x minus 3y equals 8 and having the equation of a straight line, which I don't even see, but I'm trusting that it's there, and negative 3x plus 10y equals negative 15, and having the equation of a straight line, and searching for the point where they intersect, and figuring that that's got to be the point 35.9. If it were as simple as that, the graphical method probably be a lot shorter, a lot sweeter than either the substitution method or the elimination method. Hopefully it won't seem awful, but using the graphing calculator, and I'll fire that up too. Oh, there it is. It's already awake. Using the graphing calculator, we have to solve these for y. If we want the calculator to graph them in function mode, we have to solve them for y. So we take x minus 3y equals 8, subtract 8, subtract 8, negative 3y equals negative 8x plus 8, divide both sides by negative 3, y equals negative x divided by negative 3 plus 8 divided by negative 3, y equals, 1/3, x minus 8/3. And the other one, negative 3x plus 10y equals negative 15. Add 3x, 10y equals 3x minus 15. Divide both sides by 10. Y equals 3x divided by 10 minus 15 over 10. So y equals 3/10 x minus 3/2. However much work that is, that's something below a college algebra skill. I know you knew how to do that when you registered for this class. Not something that we learned in here. But what we have to do is graph each of these. Y1, you want to say that equals 1/3 x minus 8/3. And I guess if we're typing it into the calculator and not using the fancy fraction feature that the new TI-84 pluses have, just 1 divided by 3 times x minus 8 divided by 3, and 3 divided by 10 times x minus 3 divided by 2. Then we can look to see where these intersect. Y equals, clear, type them both in, y equals. The challenge is finding a viewing window which will enable us to find the solution. Because if we zoom 6, the lines are going to look like they're almost parallel. Those would just about pass for parallel lines if we didn't know different. Because one of them has a slope of 0.3.
Why did your slope different?
It might be the viewing window. Did you zoom 6? Or is it, does that look a little bit different? I would try zoom 6 and then press y equals and compare this and see if this looks the same as what I've entered. It looks better? Okay. Zoom 6. Probably just the viewing window. They kind of look parallel. One of them has a slope of 0.3. The other one has a slope of 0.33333333333 dot dot dot. So they're kind of close together. Not much different between the slopes. A zoom out might help. Zoom, I suppose when in doubt, you could zoom out 3 or 4 times, but zooming out is just going to make them look that much closer together probably. Maybe one more time. I'm just going to press enter again. I did a zoom out, and then it wants you to press enter again. Doesn't zoom out until you press enter again, because it needs to know what you want the center of the new viewing window to be. So I'm content for it to stay the origin. So I'm going to press enter yet again. let's look at how big this viewing window is. Each time you zoom out, I think it quadruples. I think it quadruples the difference between the X-min and the X-max. So we've multiplied it by 16 now. So whereas we did have negative 10 to 10, negative 10 to 10, it's now negative 60 to negative 160 to 160. So plenty big to have the point 935 in it. Probably a little too big. I think I could have gotten this with our negative 40 to 40 viewing window. But if I go with the 10 there for X scale and the 10 there for the Y scale, we can take another look at this. How do I find the point where these graphs intersect? Calculator will do it at this point since it's actually in our viewing window. How do we do that? Find the point of intersection. Second calc 5. And they're just two curves, so selecting the first curve and the second curve, and there are no domain issues. Each one is defined for every point between the X-min and the X-max. So press enter to select the top line, press enter to select the bottom line, and for a guess, your guess is as good as mine, press enter. I've selected the origin as a guess, and it searched and quickly found the point 35.9. So there it is. It would be difficult for me to put a problem just like this on the test with the slope so similar because it looks like you're just sketching the graph of the same line. It's freehand. It would be very difficult to distinguish between those two lines, but you probably could sketch something that looked like that and put a point in the first quadrant somewhere. Label it 35.9. And the solution set here, here's where you say, Mr. Mizell, really? Really? Because when we were solving equations in section 1.6, I made a really big deal of the fact that we were using the calculator to find the value of x. We graphed y equals the left-hand side and y equals the right-hand side, and we used the intersect feature to see where the left-hand side and the right-hand side had the same value, and we were looking for that value of x that made that true. And so I said just the x coordinate. Don't put that y coordinate on there. You lose points. If you put the y coordinate on there, just the x coordinate. In this problem, it's a different problem. It's not solving a single equation in one variable. It's solving a system of two linear equations in two variables. So in this case, the solution set is not 35. The solution is not 35. It's the ordered pair, 35, 9. You need the x and the y, and that's what makes up the solution set. So in a case like this, I'm definitely looking for 35, 9 enclosed in some set braces that hopefully look better than that. There we go. And if I were going to sketch the graph, I guess I would do something like that. Whoa, a little better than that. What, like that and that? I can't see how I can take off any points if you give me something that looks like that. You know, label the point. Yeah, okay, I know the picture that you're looking at on your calculator. You did the right thing. Doesn't have to be artful. It's certainly not when I do it. All right. That was example 1. Okay. Example 2. It says use the substitution method. We can use any method you want for this. This is just here to showcase a different case. First one was case 1, where there was a unique solution to the system. This is case, I think this is case 3. I think it is. I think this is case 3, and I think we're going to expect infinitely many solutions to this. If we use the substitution method, step 1 is we would solve x minus 3y equals 5 for x, and we get x equals 3y plus 5. And then step 2, we would substitute 3y plus 5 for x in the equation. Negative 3x plus 9y equals negative 15. And when we do, we get negative 3 times 3y plus 5 plus 9y equals negative 15. And the natural thing to do is solve. So we solve for y, and what happens? We simplify, the y terms cancel, and we get negative 15 equals negative 15. True or false? True. True. But what's y? Well, it doesn't give us a specific value of y. That may seem to indicate that doesn't matter. Maybe if we could pick a y, any y, and we could come up with a true statement, and that actually turns out to be the case. For any value of y that we choose, we'll get a corresponding value of x, and that ordered pair will satisfy both of these equations. When we do the substitution method, and we simplify, and the variable terms cancel, just leaving us with a true statement, an identity, it means it's a consistent system, but with dependent equations. This is case 3. Consistent with dependent equations. But it does mean there's more work to be done, because we've got to write the solution set, and it may very well not be enough just to say infinitely many solutions. That's not to say it's all points in the plane, but it's to say that it's every point on this line and every point on this line, and those just happen to be the same line, so we need to do this. So 3 ways to do it, in increasing level of difficulty perhaps. We could say it's a set of ordered pairs of the form x comma y such that x minus 3y equals 5. That's one way to do it. Pick which equation you like better, write it down. Say, set of all points on that line, that's the solution set. Done. But we're not done, because I think Alex is going to want a little bit more. I think it'll probably say maybe something like this: the set of all ordered pairs of the form x comma y such that y equals blank. You know how Alex has the box that you have to fill in. You've got to put stuff in the box. I think it's gonna want us to put stuff in that box, and the stuff is what we get by taking the equation and put it in a slope-intercept form. Just solving for y in terms of x. So in slope-intercept form, if you have y equals, well, that's what we're going for, right? If we have x equals negative 3, darn it. Copy and paste. X minus 3y equals 5. Negative 3y equals negative x plus 5. Y equals 1/3 x minus 5/3. Is that correct? That's what goes in the box. Not the y part, not the equals part, just the 1/3 x minus 5/3 part. It's a set of points in the plane where if you look at that point, the y-coordinate is negative 5/3 of a unit less than 1/3 of the x-coordinate. That's the relationship between the coordinates of ordered pairs that satisfy this equation, the system of equations. It would have been easier if Alex had done this: the set of all ordered pairs of the form x comma y such that x equals a box. Who knows, it might. What if it did? What would we put in that box? I claim it's easier. Is it easier? 3y plus 5. Here we go. 3y plus 5. So, might be necessary, even in a case where there are infinitely many solutions, to take one of the equations, solve it for one of the variables, and then put the right-hand side in that box. We need an inconsistent system. That's not one. I don't want that. I don't like that. That was ugly. Let's do something nicer than that. Here we go. Here's our inconsistent system. Example 4. There are plenty of ugly examples later on, so I didn't see the need to do example 3. Example 4, if we're using the elimination method, you want to eliminate the x's or the y's. Trick question, of course. The x's. The x's. So we've got an x, we've got a negative 3x. So we need a positive 3x to go with that negative 3x, so they'll cancel. So multiply both sides of the top equation by 3. I'll put a 3 there, 3 there. And when we rewrite this, we get 3x minus 3y equals 21. And then copy the bottom equation, negative 3x plus 3y equals 2. And we add the two equations together. And we get 0x plus 0y, which is 0 by the way, equals 23. True or false? False. False. Which would seem to indicate what? Inconsistent. No solutions. Inconsistent system, no solutions. Parallel lines is what we're dealing with here. If we graph these and we use the graphical method, we get parallel lines. No matter how much we zoom out, they're not going to intersect. So this one is easier in the sense that we don't have to put a lot more work into it. We need to indicate the solution set somehow. You could indicate the solution set by writing the empty set. You could indicate the solution set by saying no solutions. That would do it. And just for reference, I'll say inconsistent system. And I'll also say parallel lines. All these things are true, but if the problem says solve, what it means is find the solution set. So looking for an answer to a problem, looking for something like that. Yes?
When it comes to the test, and if we come to a true statement, do we put infinite answers, or do we just?
If it's an identity on the test, I guess I've been just kind of saying, well, this is what Alex is going to want. This is what Alex is going to want. If you're wondering what Mr. Mizell is going to want, I'm going to want any of these, even if you put this one, unless, I mean, I haven't made out the test yet. I mean, it might, I would be prepared, because I know Alex is asking this, I would be prepared to deal with a situation like this. I wouldn't expect you to kind of just do that without any guidance. But if I say, okay, write the solution set in the form, the set of all ordered pairs of the form x comma y such that y equals a box, and I put everything there and leave you an empty box, then I'm going to want you to be able to fill in that box. Yeah. If I didn't write all that out, if I just said solve, and that's the only direction you had, I would think it would be perfectly fine to give me something like that. If I just said solve, because that's the solution set. That's a legitimate, valid way of writing a solution set. It would not be enough just to say infinitely many solutions. That's not specific enough. It's true, but it's not specific enough. Need an application. Ah, here we go. Ms. Smith, invested $23,000 in two accounts. One yielding 5% annual interest, the other 11%. 11%, maybe more risk involved. That's why I should put some of it in that one. Maybe the fact that was more risk involved is why she put as much as she did in the 5% account to protect it. Maybe the 11% account wasn't FDIC insured. I don't know why. She put some in the 5% account and some in the 11% account, but that's the way it went down. At the end of the year, she received a total of $1,510 in interest from those two accounts. What we're trying to see is the breakdown. How much of that $23,000 went into the account paying 5%, and how much of the $23,000 went into the account paying 11%. And if we got enough information to do this, I don't know why she didn't keep better records. We could just check her statements and see how much went into each account. But I think based on the limited incomplete information we have, this is enough to figure this out. So we're going to let X be the amount invested in the account paying 5% annual interest rate, so what that is, and then let Y equal the amount invested in the account paying 11%. Close to Bernie Madoff numbers there, but maybe there was less risk perhaps than that. Two equations, two unknowns. There's a nice one variable approach to this, which I used to do once upon a time. But in the context of these systems of two linear equations and two unknowns, we've got our two variables here, and we just need two equations to relate those variables. So what's one? Well, if we know she invested, let's say she invested $20,000 in the account paying 5%, right? Then how much did she invest in the other one? $3,000. Because we know that if we were to take the two amounts and add them together, we should get what? $23,000. So that's one equation. It's easy to come up with based on the given information. So just on the principal that was invested in each account, we add those two amounts together, we get $23,000. The other equation has to do with the interest. We've got the total interest. So if we could somehow express the interest that the 5% account yielded in terms of X, and the interest that the 11% account yielded in terms of Y, and add those together, that should add up to $1,510. So expressed in terms of X, the amount that was actually invested in the account paying 5%, how much interest did that account pay? Yeah, we need that. In fact, what we need is the simple interest formula, right? Simple interest formula. If we want to calculate the amount of simple interest paid by an account where there's money invested for a certain amount of time, and it pays a fixed interest rate during that time, what is the simple interest formula? Who knows? Is that the one? That's the one. Simple interest formula. Principal, interest equals principal times rate times time. Now the principal is X. X dollars goes into the account paying 5%. The rate is 0.05. 5% annual interest rate. And the time, 1 year? 1 year, there it is. T equals 1. So it's just the rate times the principal, basically, since the time is exactly 1 year. So we take the 11% rate and multiply by the principal. Invested in the account paying 11%, and we've got expressions for the interest paid by each one. Add those together, and that should be 1510 never mind the point. Let's just call it 1510. I had that looking like $15,000 for a moment. Substitution method, elimination method, or want to throw caution to the wind and use the graphical method? Elimination method. Elimination method. Now, if you want to do the elimination method, are you thinking take this x and turn it into negative 0.05x? Or are you thinking maybe turn this one into a 5 and turn that one into a negative 5? What's the plan? There's some good ways to do it using elimination method, but what's a good approach to this? We get rid of the decimals. We can get rid of the decimals if you like. Multiply both sides by 100. That would do it. And then we've got a 5x and a 1x, and change the 1x to a negative 5x. I actually like the elimination method here. I think it's an underused method. The natural inclination, I think, would be to maybe solve the top equation for x or for y and use substitution. But I think the elimination method is an underappreciated method for this type of problem. So I'm gonna run with it. We take the bottom equation and call that 5x plus 11y equals $151,000. And take the top equation and say that's negative 5x minus 5y equals, calculator time. Negative $115,000. I think it's a great approach to it. Add the two equations together, and we get 6y equals 151,000 minus 11 minus 5. 11y minus 5y. You get 6y. And then subtract 115,000, and we get that's equal to $36,000. And after the x is eliminated, at a glance, we could tell that y equals $6,000. Divide both sides by 6, and we've got it. And by substituting into the top equation and subtracting 6,000 from 23,000, we get that x, whoa, that's plenty of zeros. X equals $17,000 if those two add up to $23,000. Those two add up to $23,000. We need the number that when you add it to $6,000, you get $23,000. I believe that's the one. So it would appear that she's putting the lion's share of the investment in the, we hope, conservative investment, since it's only paying 5% compared to the other one, and to try to bolster her investment a little bit without risking everything, putting the other $6,000 into the 11% account and hoping for the best. Maybe it also is a reasonably safe investment. As a quick check, now again, if we've not made a mistake, this is the correct solution to this. $17,000 in the account paying 5% and $6,000 in the account paying 11%. But just to check it, we could calculate 0.05 times $17,000 and see exactly how much interest she would have earned from that $17,000 and get that that's $850 interest. And we could take 11% of $6,000, and I'm guessing that's probably $660. Is that the right order of magnitude? Not 66 bucks. The 660 bucks. 0.11 times 6,000. Yeah, $660. So if we add those together plus 850, we get $1,510 total interest in the account if she distributed the funds this way. So that's kind of a check to what we have. Of course, the answer we're looking for is, if you write it in words, that would be ideal. I haven't left myself enough space to write it really like it should be written. I would say Ms. Smith invested $17,000 in the account paying 5%, and she invested $6,000 in the account paying 11%. That's how we'd say it. I probably have enough room there. I just don't feel like writing it down. That's the thing. I'm saying it out loud. Is there another application? Maybe, possibly. We ought to do an Alex problem, right? Let's do an Alex problem and see if it gives us something crazy to do, because that's ultimately what we'll be suffering through. Let's go there. Is Tuesday, Thursday here? No. There we go. Student view. And, oh goodness, I can't remember. Have I worked any Alex problems in class before? Yes. Clicking on the review button?
Yeah.
Yes, okay, good. So I don't need to reset the student view. Just open it up and click on the review button. And there it is. All right. What are you thinking? We probably just did a tax rate or interest problem. I don't know that I care for the percent mixture problems. How about a value mixture problem? Let's do a value mixture problem. Oh yeah, this is nice enough. Family has 2 cars. First car has a fuel efficiency of 35 miles per gallon, and the second has a fuel efficiency of 40 miles per gallon. During one particular week, the 2 cars went a combined total of 2,025 miles and consumed a total of 55 gallons of gasoline. That's a good bit of driving for 1 week. And a lot of gasoline. How many gallons were consumed by each of the 2 cars that week? I think it makes sense that this is information we might have, because if you're keeping close track of the odometers, I don't know who does that, but if you're keeping close track of the odometers on the 2 cars, you could just kind of compare the difference for weekly, Sunday to Sunday or whatever, and that's information you would have readily available. Actual gasoline consumption might be a little trickier unless you filled both cars up at the beginning of the week and then filled them up again to see how much gasoline. But if you did that, you'd probably know how much each individual car used, right? So this problem would be moot. I mean, we would have that information. Nonetheless, I think we've got information to do it in case any of that might be missing. So let X be the number of gallons of gasoline used by the 35 mpg vehicle, and let Y equal the number of gallons used by the 40 mpg vehicle. What's X plus Y? 55 gallons. What's our other equation?
35x is 41.
If we get 35 miles a gallon and we go X miles, no, my bad. If we get 35 miles a gallon and we consume X gallons, consume X gallons, then that tells us how many miles that we go. If we get 40 miles to the gallon and we consume Y gallons, that tells us how many miles we go. So that's the total of 2,025 miles. So the equation not a whole lot different in setup from the previous one. Probably should use a different method instead of substitution, although substitution would work beautifully here. Sorry, instead of elimination like we did in the previous example, which would work beautifully here, let's use the substitution method, which hopefully will work equally beautiful. Y equally beautifully? Yeah, adverb I think is what I wanted there. 55 minus X. 35X plus 40 times 55 minus X equals 2,025. So we take the top equation, solve it for Y, get an expression with an X in it, substitute that for Y in the other equation, and simplify. 35X plus 2,200 minus 40x equals 2,025. Combine like terms, get negative 5x plus 2,200 equals 2,025. Subtract 2,200 from both sides. Get negative 175. And then divide both sides by negative 5 to get 35. Wow. So we get 35 miles to the gallon, and we consume 35 gallons. That's not confusing at all. So 35 gallons. I shouldn't complain. I mean, Alex generated this using random values. Just a bizarre coincidence that it worked out like that. We should be able to subtract from 55 then to get the number of gallons consumed by the 40 mpg vehicle. So how many gallons? 20? There we go. So if we're saying this, and maybe I have room, the 35 mpg vehicle used 35 gallons, and the 40 mpg vehicle used 40 gallons of fuel. No. What do we say 55 minus 35 was? 20 gallons of fuel.